So in the last section, we started thinking about series as being functions in their own right. In particular, we are looking at series of the following form. So these are called power series. They are defined by a sequence of numbers and a center point, and these are indeed functions because you give it a number x and it outputs a corresponding series. So recall, these guys have as their domain either the single point, a, or the entire real number line, or a finite interval, called the interval of convergence. So, our goal in this section and the next section is going to be to take an elementary function, which is to say a function which isn't a power series, and replace it with a power series which is identical to it on its domain. So, for example, in particular, given an elementary function f, we need to find a sequence and a number such that the function is identical to the power series, provided x is chosen such that this series converges. Now, some functions can only be written as a power series. So we saw an example of that in the last section with the Bessel function, which we're going to be seeing again soon. What we are interested in, though, is the case where a power series can actually be represented as an elementary function, and vice versa. Now, we have already seen this in at least one form, the geometric series. So, consider a geometric series with a equals 1 and r equals x. So that's going to look like this. And we know that geometric series are going to converge if the absolute value of r is less than 1. Well, in this case, I'm letting it be x, so there's that. And part of the reason that the geometric series is so vastly important to us is because it's one of the few cases where we can actually write down a formula for what the series converges to. For this particular example, it's going to converge to 1 over 1 minus x, because it's a over 1 minus r. Now, this guy is actually a power series. I mean, I don't think that's too hard to see just by looking at it. In particular, for this to be a power series, we need to change the starting point to 0. Remember, if you want to decrement the starting point, then you just need to increment the index. So changing the starting point down by 1 means you have to increase the index by 1. So then you get this. And when I've written it in this form, you can clearly see that this is a power series where the center point, a, is 0, and the sequence is just the sequence of 1s. You just have a 1 in front of every term. So the interval of convergence of this guy is the interval from -1 to 1, because that's what this guy indicates. And correspondingly, the radius of convergence is 1, because the radius of convergence is half the length of the interval of convergence. So we conclude that as long as x is inside this interval, this rational function, 1 over 1 minus x, is identical to this power series. So this is the sort of result that we are looking for. We are looking for exactly this situation, where an elementary function can be represented as a power series for some values of x. It's too much to expect that this is going to work for all values of x, so this is only going to work inside some interval of convergence. Indeed, this dude on the left is defined for all x's except for x equals 1, because that's when it would try to be dividing by 0. But nonetheless, this equation only holds true for x's inside this interval. So let's actually show that in Geogebra. So here, in green, this is the function 1 over 1 minus x, right? It's a rational function. You can see it has an asymptote at 1, which is where it would be dividing by 0. And we claim that for values of x between -1 and 1, this dude is going to be identical to the power series. So focus on the values of x between -1 and 1. Okay, so we're going to look at partial sums of the power series. So the first term is 1. All right, well, not a very good approximation. It only agrees with the graph at this single point, at x equals 0. The first two terms are 1 plus x. Now you can immediately see that it's a better approximation because we're getting the tangent line. Right? This is exactly what we would get if we were asked to find the tangent line at x equals 0. And indeed, it's a better approximation because it looks like it is agreeing more with the curve in the vicinity of x equals 0. Next, add on another term to get 1 plus x squared, and it's starting to look even better. Next, it's cubic, so the sum of 1x, x squared, and x cubed, it's starting to look even better. Even better. Even better. Even better. Indeed, if we zoom in, then the two curves are completely indistinguishable from one another. Right? Here's 1 over 1 minus x. Here's 1 plus x squared, plus x to the 6th. So if you are close enough to x equals 0, if you are in the vicinity of the center point, then the two guys are indeed indistinguishable. And you can pick any value of x between -1 and 1, and like you can tell that the approximation gets pretty bad over here, but if I took this up to, say, x to the power 100, then I'm sure it would be almost perfect. Outside of this range, though, there is no hope of being able to approximate the function, because look, for instance, at what's happening for values of x less than -1. So you can see that the partial sums, being polynomials, they are varying between going up and going down. So there is a wildly divergent behavior in the partial sums over here. Similarly, to the right of 1, the function 1 over 1 minus x becomes negative, and that is also completely at odds with the behavior of the partial sums. So indeed, the approximation is really only valid between 1 and -1, and it degrades elsewhere. And it's the best the closer you are to the center point, which in this case was x equals 0. Okay, so this is the sort of result that we are looking for. So ordinary function on the left, power series on the right, provided x is in some interval of convergence. And we can use this fact about geometric series to derive other identities for other functions just by replacing the x with some expression. Okay? So replace the x with an expression, and all of this condition still remains true. So instead of writing x is in -1 to 1, that's the same as saying that x is between -1 and 1. So just for clarity, I rewrote it there. Okay, so here's a function, 1 over 1 plus x squared. We want to write this as a power series, which is valid within some interval of convergence. So our strategy here is going to be to take this guy and rewrite it so that it's in the form 1 over 1 minus stuff. Because then we'll be able to transform it into a power series. Okay, so we want to rewrite it so that it's in that form. Well, there's not too much that we need to do. Really, the only problem is that there's a plus here instead of a minus, but we can fix that easily enough. Right? Minus a minus is plus, so that works out. So this is exactly the form that we want, where stuff is taking the role of negative x squared. So now we can rewrite this as a power series accordingly, using this fact up here. So this is going to be sum, as n goes from 0 to infinity, of stuff to the power n. And we can clean this up a little bit. Because this minus sign to the power n, well, that becomes an alternator. And then x to the 2n, like so. So it's a power series that only involves even terms, but that's fine. Now, what about the interval of convergence? Well, stuff needs to be between -1 and 1 for this to work. So, in this case, stuff was equal to negative x squared. So we require -1 to be less than negative x squared to be less than 1. Let's multiply all three sides by -1. That's going to flip the inequalities around. So 1 is greater than x squared is greater than -1. So think about it. For what values of x is x squared going to be between -1 and 1? Well, let's get all this out of here. So for what values of x is x squared going to be between -1 and 1? Well, clearly, it's going to be between -1 and 1 when x is between -1 and 1 as well. So this is the same as saying that, yeah. So x squared is going to be between -1 and 1 if and only if x is between -1 and 1. So the interval of convergence is -1 to 1 again. Okay? So there we go. So here's the representation as a power series, and here's the interval of convergence. Find a power series representation for this guy. Okay, well, once again, we need to rewrite this as 1 over 1 minus stuff. So let's see what we can do. So first off, we can rewrite that to be 2 plus x, just because all of the x's are going to have to end up being in the stuff. Now, we have a 2 here. We want there to be a 1 here. So what should we do? Well, let's factor out the 2. So we get 1/2 1 over 1 plus x over 2, like so, right? I mean, of course, this makes sense, because take this 2 and multiply it back through, and you get exactly what we started with. So now we've got a 1 here, a 1 here, All we need now is the minus sign. Well, that's easy enough. We just do the same trick that we did last time. Just putting two minuses right next to each other. Okay? So, we've got a 1/2 hanging out in the front, but that's fine, because this chunk we can now turn into a power series. So here, stuff is equal to negative x over 2. So we have 1 over x plus 2, which is the function that we started with, is the same as 1/2 times the sum as n goes from 0 to infinity of stuff to the n. And then let's clean this up a little bit to make it look more like a traditional power series. So this minus to the n, that becomes an alternator, over 2 to the n. So let me write it like this. And then x to the n. And finally, if you want, you can distribute this graph back in, and all that's going to do is that's going to increment the power of this exponent. So that might make it look just a little bit cleaner. Like so. So there we go. There's the power series representation of this dude. Now, as for the interval of convergence, well, we need to take stuff between -1 and 1, right? That's the condition under which this transformation into a power series is valid. So here, stuff was negative x over 2. So multiply all sides by -1. That's going to flip the signs. Now multiply by 2. Okay. So the interval of convergence is the interval from -2 to 2. Yep. And we don't need to check the endpoints here because we already know that the endpoints aren't going to work, right? This is just, we're just adapting the formula for the geometric series to different contexts. So yeah, these guys are all just geometric series in disguise. What about this dude? Find a power series representation of x cubed over x plus 2. Okay, so don't let this worry you, because this is the same as x cubed times 1 over x plus 2. And we already have a power series representation of 1 over x plus 2, so it's just going to be that power series times x cubed. Right? So there is no additional work that needs to be done here. Literally just plug in the power series that we have already obtained. And then if you want, well, yeah, you should do this because that'll just make it nicer. We can take this x cubed and distribute it back in, and that's just going to increment this dude by 3, right? Just combine the like terms. Like so. Yep, that's all there is to it. And the interval of convergence, so since we are just taking the power series representation of this dude, where the interval of convergence was -2 to 2, that's going to be unchanged. So, yeah, interval of convergence is still -2 to 2. Okay. So, one of the reasons that we are interested in power series, so power series being series that have this very specific form, one of the reasons that we are interested in power series as opposed to some other form of series is because, as it happens, power series can actually be differentiated and integrated very, very easily. So this dude is indeed a function, right? It's a function of x. So it makes sense to ask whether this function can be differentiated and anti-differentiated. And indeed they can, and very easily, because literally all you need to do is just apply the power rule to each term of the series. So that's what's called differentiating and integrating term by term. So you literally just differentiate all of the terms, and it works. It'll still converge. Which isn't immediately obvious how to prove this, but we're not going to worry about actually proving this in this course. That would be the sort of thing that you would do in a graduate level course, is actually prove that this thing can be differentiated. In any case, yep, so this power series, if you write it out, it's c sub 0 plus c1 x minus a plus c2 x minus a squared. So if you want to differentiate this, literally just differentiate each term. So the derivative of c0 is 0, because it's a constant. Derivative of this dude is c1. Derivative of this dude, well, apply the power rule, so bring down the 2. Derivative of the next dude would be something to the power of 3. So doing the power rule, you bring down the power of 3 to get that, and so on and so on. So the general form is given here. So notice, this general form is super easy. Literally all you're doing is just applying the power rule to this dude. Take n, put it down front, and then subtract 1. That's all we're doing. The only thing you sort of have to be careful about is the starting point, because the starting point for a general power series is n equals 0, but for this formula to make sense, the starting point has to be n equals 1, and that's because this first term ended up getting nullified when you differentiated. So just be aware of that when differentiating, you just apply the power rule, but you might have to increment the series by 1, because the first term might be getting disappeared. And then anti-differentiating is just as easy. Once again, it's just the power rule. So add 1 to the exponent to get n plus 1, and then divide by the exponent, as shown. And in this case, because you're not disappearing any terms, you don't have to worry about the starting point. The starting point stays the same. And here's the constant of integration, which is just out front, because if you put it over here, that might be confusing. Another important thing to recognize is that the radius of convergence remains the same when you differentiate or anti-differentiate. And because the center point is also the same, that means the interval of convergence also remains unchanged. So actually, let me mention that. Well, actually, no, that's not true. That's not true. The radius of convergence stays the same, but convergence at the endpoints might actually change. Yeah, that's a possibility. That's a possibility. Convergence at the endpoints might change. So actually, I shouldn't say that. But the radius is the same. typo there. So the fact that power series can be differentiated makes them extremely powerful tools. So what you will find later on, if you take a course on differential equations, is you'll find that a lot of differential equations have solutions which can only be written in terms of infinite series. For example, that's how the Bessel function appears. There is a particular differential equation that you encounter when looking at vibration of a drum head, and the solution to that differential equation involves assuming that the solution will have the form of a power series, and then you can do a bunch of algebra and basically just find out that it has to be this. It has to be of this form. Okay, so if power series can be differentiated, differentiate this dude. Differentiate the Bessel function. That's easy. It's just the power rule. So, the derivative of this guy. Now, you do have to be careful with the starting point. So notice that the first term of this thing is going to be what we get when we plug in x equals 0. So when we plug in x equals 0, what happens? 2 to the 0 is 1, 0 factorial is 1, 1, 1. Okay, it's all 1. So when we differentiate this dude, the first term is going to disappear. So that means the starting point is going to have to increment by 1. But that's really the only weird thing about it. Everything else is straightforward. But aside from that, it's literally just the power rule. So take the 2n, move it out front, and subtract 1. And everything else remains unchanged. And I suppose we can clean this up a little bit by canceling one of the 2's with one of the 2's down here, but I don't really care. So let's just leave it at that. Yeah. So you may recall the interval of convergence of the Bessel function was all real numbers. So that means the radius of convergence was infinity. So the radius of convergence is unchanged under differentiation. So that means the radius of convergence of this dude is also infinity, and correspondingly, the interval of convergence is all real numbers. So since the radius of convergence was infinity for the Bessel function, we have radius equals infinity for the derivative as well. So the interval of convergence is all real numbers. Okay. Express this dude as a power series. So, coming so soon as it does after, the statement about derivatives and antiderivatives, you would think that this has something to do with differentiation. And indeed it does, because this dude is the derivative of 1 over 1 minus x. And 1 over 1 minus x is just the ordinary power series. So notice that this dude is the derivative of 1 over 1 minus x. So to get the power series representation of this, we just need the power series representation of 1 over 1 minus x, and then differentiate it. So it's the derivative of the power series representation of this dude so the first term is a constant, which means it goes away, so you have to increment the starting point, but aside from that, it's literally just the power rule. And that's that. And find the radius of convergence. Well, since the radius of convergence for 1 over 1 minus x is 1, it is the same for this dude. So yeah, not saying anything about the interval of convergence, because I don't know, I would have to check. We would have to check by using the ratio test, but I'm not convinced that the endpoints of the interval of convergence remain the same. But anyway, let's just move on. Find a power series representation for the natural log of 1 plus x. Okay, so is this guy the derivative or the antiderivative of something? Well, indeed it is. So notice that, I mean, the natural log was defined to be an antiderivative. So notice that natural log 1 plus x is the antiderivative of 1 over 1 plus x. So all we need to do is find the power series representation of 1 over 1 plus x and then anti-differentiate it. Okay. Incidentally, while we're here, what is the power series representation of 1 over 1 plus x? Well, we would want to write this to be in the form 1 over 1 minus stuff so that we could use the geometric transformation. And that's not too hard. All the ingredients are already there. So in this case, stuff is negative x. Yep. Like so. So why does this have a radius of convergence of r equals 1? Well, because the radius of convergence of the geometric series is r equals 1. And here the stuff is negative, but whatever. Plopping a negative sign in front of it isn't going to change the magnitude of the interval. So check that for yourself if you want, but I think it's clear. Anyway. So we need to anti-differentiate this power series. Which, well, we just apply the power rule. And since we're anti-differentiating, we don't need to worry about changing the starting point. Sorry, I'm looking for the pause button. I can't seem to find it. I didn't want to cough while streaming. Shoot, I'm going to have to find that. I recently updated OBS, and now things are slightly different. Anyway. Okay, let's see. So, yeah, just power rule. That's all there is to it. Well, there's a little bit more to it, in that when you're doing the antidifferentiation, you have to add in a constant of integration. So that begs the question, what is this c going to be? Well, that's not too hard to figure out. Let's just plug in a value of x and see what happens. So let's plug in, say, x equals 0, right? Let's pick an easy one. Because then, on the left, we get natural log of 1, which is just 0. And on the right, we get c plus oh, 0 to the power n plus 1. Well, that's interesting, because natural log 1 is 0. Here we have a series of nothing but zeros. Cool. So c is equal to 0. So we conclude that natural log of 1 plus x is the same as 0 plus that sum. And the radius of convergence is 1, because antidifferentiating doesn't change it. Okay, find a power series representation for the Arctan function. All right, well, going with this same strategy that we've been doing, let's write down Arctan as an antiderivative. Right? I mean, Arctan is the antiderivative of 1 over 1 plus x squared. So, all we need to do is antidifferentiate, I'm sorry, by the way, antidifferentiate the power series representation of 1 over 1 plus x squared, which, conveniently enough, that was one of our examples. Yeah, that one. And the radius of convergence is half the length of this dude, so the radius of convergence is 1. So let me just copy this guy, getting ready for that. Yeah, so it really is just that easy. So add 1 to the exponent to get 2n plus 1. And then we have our constant of integration. So we need to figure out what this constant of integration is. With any luck, it's going to end up being 0. So once again, let's just plug in a value of x and see what happens. X equals 0, in fact, because that's going to make this entire series just disappear. Well, is it actually going to make it disappear? Because if the first term of the series is a constant, then that's still going to be there. So you know what? That is a good point. If the first term of the series is a constant, then plugging in x equals 0 won't make it disappear. So let's actually write out the first few terms of this thing, just to get a better sense of what it looks like. So when n is equal to 0, we have 1, 1, 1, 1, 1. So that's x. When x is equal to 1, okay, when x is equal to 2, okay. So this guy has a pretty nice pattern. Oops. So actually, yeah, that's nice. It's nice to see that the power series representation of log 1 plus x has this sort of appealing pattern to it. I mean, it's just alternating signs and reciprocals. And now, indeed, you can clearly see that when you plug in x equals 0, all of this is going to disappear. So, like so. What about this dude? So let's see, when x is equal to 0, we get, so it's just x. When x is equal to 1, when x is equal to 2, so again, another nice pattern here. Which I should point out. I mean, it's just cool that such a pattern would exist in the first place. So here you can see, again, the signs are alternating, and it's just all the reciprocals, but now it's just taking the odd reciprocals, whereas in the natural log case, it was taking all the reciprocals. So that's interesting. And indeed, we can now see that when we plug in 0, we get all zeros here. So arctan of 0 is 0, so c is 0 again. Convenient. And the radius of convergence was, what was it for 1 over 1 plus x squared? It was 1. Okay. So anti-differentiating doesn't change that. Okay. So we have seen that for certain flavors of function, functions which are adjacent to geometric series in some sense, we can, without too much difficulty, rewrite them as power series. And one of the immediate utilities of rewriting them as a power series is that differentiating or anti-differentiating them becomes completely trivial. So that means that we can use power series to do integrals, right? Rewrite the integrand as a power series, and then you can anti-differentiate by using the power rule. Indeed, 1 over 1 plus x to the 7, I don't know how I would anti-differentiate this. I don't even know if it's possible. But if you replace the integrand with a power series, then it becomes completely trivial. So it's just that simple. So first off, let's figure out what the power series representation of this thing is. I mean, we can rewrite this as 1 over 1 minus stuff pretty easily. Literally, that's all you need to do. So this is going to be... So the stuff in this case is negative x to the 7. So that negative becomes an alternator. like so. And the radius of convergence is... What is the radius of convergence? So we need stuff to be between -1 and 1. So in this case, stuff is -x to the 7. Okay, yeah, so that's equivalent. I mean, take the negative sign, that's going to flip things around, and then take 7th roots. But the 7th root of 1 is still 1. So that's equivalent. I guess they're not asking for the radius of convergence, but whatever. It's a necessary component of dealing with series, is to figure out, when precisely it is that it's going to converge. Okay, so now we can anti-differentiate. So just add 1 to the exponent and then divide. So 7n plus 1, x to the 7n plus 1. Like so. And constant of integration. And that's it. That's all we need to do. Because this is an antiderivative, we just leave the c here. There's no additional work that we need to do to figure out what that is. Yeah, it's just that easy. There's a tremendous amount of work to be able to justify getting here in the first place, but now that you know that you can take functions and replace them with polynomials, essentially, really that makes differentiation and anti-differentiation trivial. It's part of why, that's why this is the most important part of Calculus 2. Yeah, no, this is just a super, super useful technique. Okay, well, now that we have an antiderivative, in some sense, let's figure out what this definite integral is. And it's because we're going to be evaluating an infinite series, by necessity, we're going to have to get an approximation. So we want the approximation to have an error of less than 10 to the negative 7. So we'll use one of our estimation tests to do that. Okay. So this is going to be, so we know the antiderivative is this. So it's going to be this, but evaluated between 1/2 and 0. And before we move on, let me just, for the sake of interest, write out the first few terms of this dude, just to get a better sense of what it looks like. I keep forgetting to do that, but it's not strictly necessary, but I do think it helps to build an intuition as to what's going on here. So let's see, when n is 0, we get x, then it's an alternator. When n is equal to 1, when n is equal to 2, 2 times 7 is 14, plus 1 is 15, and one more. When n is equal to 3, 3 times 7 is 21. Okay, and it keeps on going from there. So one of the reasons why I did that is because I want to know what this series looks like when I plug in 0. And indeed, you plug in 0, you get nothing but zeros. By contrast, you plug in 1/2, and you're going to get a series. What is going on here? What am I doing? Oh no, I've lost it. Okay, there we go. So you plug in 1/2, and you get, well, 1/2 to the 7n plus 1. Like so. Okay, so now we need to evaluate this series. Well, how can we possibly do that? Just by adding up a whole bunch of partial sums. We want it to be accurate, though. So notice that this is an alternating series, so we can use the alternating series estimation theorem. And in particular, I want to determine how many terms of the sum to take. So recall the alternating series estimation theorem, which says that the remainder upon taking the kth partial sum is less than or equal to the k plus 1th term of the series. So in our case, so this is what you get neglecting the alternator. So for us, that's going to be 1 over 7 k plus 1 plus 1 like so. Literally just replacing n with k plus 1 here. So let's see. That's 7k plus 7 plus 1, so plus 8. Yeah. Okay. Now, we want this error to be smaller than 10 to the negative 7. So take k large enough so that the following inequality is satisfied. So we want this dude to be less than 10 to the negative 7. Because that's going to guarantee that the error is smaller than 10 to the negative 7. Now at this point, it would be nice if we could solve this inequality for k, but the combination of an exponential and a rational function here is making that kind of iffy. So I think we're just going to have to start plugging in numbers. So, yeah. So let's see. I'm gonna grab my calculator. So I'm just gonna. All right. I was gonna say I'm gonna pause the recording, but I don't know where the pause button went. Whatever. It's on YouTube. You can just skip forward, because I'm just gonna be doing calculations now. In silence. Horribly, horribly unprofessional behavior. Okie dokie. Oh, well, that's fast. All right, well, I plugged in k equals 1, and already it's a very small number. So, 2.03 times 10 to the negative 6. All right, well, that's not quite small enough. This is the left-hand side I'm plugging k into, naturally. Oh. All right, so k equals 2 is going to do it. Yeah, because I plug in k equals 2 and I get 1.08 times 10 to the negative 8, which is indeed smaller than 10 to the negative 7. Okay, so taking partial sums up to k equals 2 will get the desired accuracy. So then why is it that in the book they did k equals 4? Why? Oh, yeah. Sorry, I'm confusing myself here. Skip. Next. Dislike. Unsubscribe. Oh, I think I get why I'm confused. Because the starting point here is at n equals 0. And in the statement of the alternating series estimation theorem, the starting point from the series is 1. I knew that was going to be a problem at some point. But the stupid book insists on starting everything at 1 up until this bit on the power series, when now everything shifts to 0. And that means everything is off by 1. Okay, so that means... Gosh darn it. Gold darn it. So that means, if I really want to be pedantic, which I do, I have to change this to be n equals 1. So if I want to increase the starting point by 1, then I have to decrease all the indices. Ugh. So that's 2 to the 7n minus 7 minus 7 plus 1. So that's minus 6. Does that make sense? Yeah, because when I plug in n equals 1, I get 7 minus 6, which is 1. So that's fine. And 7n minus 6, like so. Okie dokie. So here, b sub n is equal to this bit. So when I plug in k plus 1, that's going to be like so, just replacing n with k plus 1. So 7k plus 7 minus 6 is plus 1. Plus 7 minus 6. All right. So now we start plugging in numbers again. Okay, so if I just take the first partial sum of the series, and everything's going to be the same, it's just going to be shifted by 1. So okay. 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 So if we just take the first term of the series, then the error would be this. If we take the second term, it would be this. If we take the third term, it would be this. So that means that we need to add up only the first 3 terms of the partial series. Yeah, we only need to add up the first 3 terms of the sum to get the desired accuracy. But why the heck in the book is it adding up 4 terms? We only need 1 term. Or I mean, we only need 3. It even says that if we stop after adding the term with n equals 3, the error is smaller than the term with n equals 4. Yeah. So just add up the first 3 terms. I don't understand. I don't understand. I don't know what the book is trying to say. Whatever. Let's just add up the first 3 terms and then call it a day. You've all stopped watching this eons ago, I hope. I hope you're not watching this. What an embarrassment. If I ever want to use these videos again, I'm going to have to re-record them. But, you know, this is what happens. So to get the desired accuracy, add up the first 3 terms of the series. Okay, so when n is equal to 1, this is 1 over 7 minus 6 is 1. So 1 over 2. When n is equal to 2, it's going to alternate. So 14 minus 6 is 8. When n is equal to 3, 21 minus 6 is 15. So we end up with, and by the way, let's not forget what the point of this was. The point of this was to integrate this, compute this definite integral numerically. Okay. So finally. Oops, hang on. troubleshooting. Okay. Sorry, I'm wrangling my calculator right now. All right. Okay, and there we go. And we know that it is accurate to 7 decimal places because the error is less than 10 to the negative 7. Is that right? Is that how that works? I don't know. Let's get rid of 1 just to be safe. We know that it's accurate up to 6 decimal places because the error is less than 10 to the negative 7. All right. Enough with this. That's all for now.